Today I want to talk about kaons and onium theory. Kaons are one of the most important of the lighter particles to any particle model in physics. And you have probably heard about quark theory and maybe know a little bit about kaons and quark theory. So I'm going to talk about the onium theory that I've developed based on work by Milne, Feynman, and Sternglass. And at first, kaons are a real challenge because they have some unusual properties. First, the K naught has two different types. It has a K short and K long, which are short and long lifetimes. So you have two different particles with the same mass and the same composition, but a different lifetime. So you have to be able to explain physically why that is. And what's interesting is you can take a beam of kaons and the K shorts will decay, leaving the K longs. But if you run it through matter, some of the K longs will convert to K shorts. So that tells us that the composition really is the same. And then we also have the process that the K longs can decay to seemingly matter or any matter type. So in the theory, they say that there's matter K longs or matter K naughts and antimatter K naughts. In actuality, if you look at the decay of the K shorts, it doesn't show any preference. And that's important to how we understand the matter. And as far as matter and antimatter preference goes, we'll see that the K long predominantly decays to muon and a pion. Or an electron in a pion. And so depending on whether the electron is and muon are negative or the electron and muon are positive determines whether it's considered a matter or an antimatter type kaon. And that really tells us a picture of what the K long is. It decays to a muon and a pion, and that's most likely what it is. And within the Onium model, that's the way we proceed. We look at the decay products and we say that's the most likely composition. Sometimes you have to look at the most common decay products. The first two or three usually give a good hint. Sometimes you have to look at the more complex ones so that you account for all the decay products that come from a particle. Sometimes they have a lot more pions coming out of it, and you have to account for each one. So it's not easy to interpret, and it's been a challenge for me. And while the K longs have a muon-pion combination, the K shorts most commonly decay to two oppositely charged pions, which also tells us the most likely composition of the K shorts. And so then the challenge is deciding or figuring out why they have a shorter lifetime. Now, within the quark theory, they say that the matter K naught is a down quark and an anti-strange quark, while the antimatter K naught is an anti-down quark and a strange quark. So you have two mirror combinations. But one of the things here is that the K naught isn't really matter or antimatter. Because if you run out the entire decay chain, including the decay of the pion that it decays to, there's an equal number of electrons and positrons inside a kaon. So it's not really matter and antimatter at all. It just has a bias in the way that it decays. And like I said, that's a pattern that tells us that we have a muon that's either positive or negative within the kaon. And so coming up with the matter and antimatter kaon in the quark model is kind of ridiculous on its face because there really isn't an antimatter version. There's just one version. It just has its composition is slightly different. And then there's also the issue that they don't actually exist. There isn't an actual matter K naught, or antimatter K naught. What there are the K short and K long. Those are the ones that really exist. And then briefly, the charged kaons are said to be an up quark and an anti-strange, or the anti-up and a strange. So they have a matter and antimatter version too, which makes sense because they can have an electron or a positron combined with two pions, or a muon-pion combination. And that's what the decay products tell us the general composition of the kaon is. Two oppositely charged pions, or a muon-pion pair, and then an electron or positron in the middle. See the model there. So, getting back to the K naught, we have this nonsensical formula of you take a K naught minus an antimatter K naught divided by the square root of 2. But of course, if you put a D and an anti-D together, they annihilate, and a strange and anti-strange together, they annihilate. So really, it's 0 divided by the square root of 2. And then if you add them together, you get either 0 divided by the square root of 2, or you get 2 times the kaons divided by the square root of 2. If you try to do an actual physical interpretation, and not just a wave superposition type modeling idea, the physical interpretation doesn't work. This equation makes no sense. And dividing an elementary particle by the square root of 2 makes no sense. Subtracting an elementary particle from another elementary particle makes no sense. And within the quark model, there's 7 different particles that are modeled this way, including the most elementary one, the neutral pion. And I talk about that in my video, the neutral pion, and then I also have another video on the charged muon and charged pion that are good to watch if you haven't watched them previously. And in particular, the muon-pion information from that video goes in the one I'm going to talk about next. Within the Onium theory, the muon and charged pion are composed of a neutral pion and an electron or positron. And the neutral pion is relativistic positronium. So it has an electron-positron pair rotating at an orbital velocity, a high relativistic orbital velocity, which gives it relativistic mass, which is where the mass energy comes from. And the mass is essentially the 2 particles times 70 MeV per c squared, because within the mesons and baryons, their mass energies are quantized at 70 MeV per c squared and or 35 MeV per c squared. So the way the mass ends up being calculated is you have 2 pions in relativistic orbital velocity, or a muon and a pion. Each one has 3 particles, so there are 6 particles total. And within the kaon, they're quantized at 35 MeV per c squared, so you have 6 times 35 equals 210. So you have 210 MeV per c squared in relativistic orbital mass energy of the kaon, plus the mass of the 2 pions, gives you 490 keV per c squared, which is roughly the mass of the kaons. They have a little bit more mass because the 2 neutral pions are counter-rotating, so that they're magnetically coupled, which gives it slightly more energy. Those are details that still need to be worked out within the Onium model. And so basically we have the neutral kaon with 2 pions, the K long with a muon and a pion, and then or neutral kaons can also have 2 muons, K long with muon and a pion, and then the charged kaon with generally a muon and a pion, and then an extra electron and positron in the middle. But if you break that down, you have 2 oppositely charged neutral pions orbiting with each other. And if you have a 2-pion combination, you have the electron, because they're flipped, you have an electron and positron rotating in opposite directions, which causes them to annihilate quickly. Because the muon gets its lower energy mass because the extra electron or positron is orbiting in the same direction as the pion, the internal neutral pion. And so if you have 2 muons, you also have this collision between the electron and positron. And something interesting happens when you have a muon and pion, because the muon orbits with its pion, and the pion has the outer electron orbiting against it. When you flip one over and put them together, the electron and positron end up orbiting in the same direction, which allows them to be stable for longer. And that's why a K long is a muon-pion combination, which matches its decay products. And so within the Onium theory, we can very simply explain the decay characteristics and why there's a K short and K long. Then the remaining question is, how are the 2 K naughts, the K short and K long, how do they have the same mass if one has a muon and a pion and one has 2 pions or 2 muons? And that's because the muon gets a reduced energy because the muon is orbiting in the same direction as the pion. But when you have 2 pions in the middle counter-rotating, there isn't a preferential direction, so you don't get a reduced mass energy for one of their orbits like you do within the muon. And so for that reason, whether it's a muon-muon combination, a pion-pion combination, or a muon-pion combination, they all have the same mass energy. And although there's a slight difference at approximately 8 orders of magnitude, but for the first 6 orders of magnitude that are most commonly cited, the mass energy is the same. So once again, the Onium model clearly explains what's going on. And this is based on physics from the 1960s that's been ignored by standard model theorists that are trying to promote the nonsensical quark model. Anyway, I hope you enjoyed my video about kaons and learned something about the Onium theory, and also learned something about why the quark theory is so bad. If you like my video, please like, share, subscribe. And if you're interested in supporting my research, I have a book on the Onium theory, Goodbye Quarks, the Onium theory, and I'll link to a couple papers below as well. And then if you're interested in my quantum field theory research, I have a couple books on quantum field theory as well. And by buying my book, you support my research. I'm an independent researcher. And I also have a Patreon account if you feel like doing that. So I appreciate you watching. Thanks.